हेलो एवरीवन। मेरा नाम अभिमन्यु सिंह है और मैं केमिकल इंजीनियरिंग आईआईटी के का फर्स्ट ईयर का स्टूडेंट हूँ। और आज मैं पढ़ाने वाला हूँ ग्रेविटेशन चैप्टर, उसका ये पहला लेक्चर है। तो स्टार्ट करते हैं। मतलब ग्रेविटेशन एक फ्यू ऑफ द फंडामेंटल फोर्सेस में आता है, जैसे इलेक्ट्रोस्टैटिक फोर्स हो गया और ग्रेविटेशनल फोर्स आ गया। ये सारे फंडामेंटल फोर्सेस होते हैं नेचर में जो एग्जिस्ट करते हैं। इन्हीं इन्हीं के कारण से मतलब बाकी अदर फोर्सेस रहते हैं। तो ये सारे फंडामेंटल फोर्सेस होते हैं नेचर में। तो ग्रेविटेशनल फोर्स भी एक फंडामेंटल फोर्स है। और तो और ग्रेविटेशन ही है, मतलब ग्रेविटेशन से ही हम प्लैनेटरी मोशंस वगैरह डिस्कस करते हैं और बहुत सारे ब्लैक होल्स वगैरह के बारे में भी पढ़ते हैं। तो ग्रेविटेशन का बहुत ज्यादा एप्लीकेशन है। और तो ग्रेविटेशन सबसे पहले बहुत सालों से प्लैनेट की स्टडी हो रही है। और सबसे पहले जो इनिशियल थ्योरी आई, वो जो सबसे पहले थ्योरी थी, सबसे पहले लोग मानते थे कि people used to assume that the earth is revolving around the sun. So this was known as the geocentric theory. Geo means earth and centric means center. Like earth is in the center, as you can see in this like photo, that earth is in the center and every other planet, even sun, Neptune, Mars, is revolving around it in different orbits. This was like highly supported by the church and the various authorities, and they used to assume that the earth is most supreme planet, so every other thing should else revolve around it. So this was earlier theory, which was short wrong, as we know that earth rotates around the sun, not the other way around. So this was given by Aryabhatta in India around 5th century AD, and it was also given by Copernicus in Europe 16th century AD. And when Copernicus gave this theory, like the Earth is revolving around Sun in circular orbit, he was highly opposed by the church and the various other authorities during that time. So finally, it was came to know that our system is the sun-centered solar system. That like the sun remains at the center, and every other planet revolves around it in orbit. And the shape of orbit, earlier it was assumed to be circular, but it is not circular, as we can see on in our next slide. As we can see in our next slide, Kepler law of planetary motion. Then we move to study towards the Kepler law. Then Kepler formulated his law for planetary motion, the law which governed the planetary motion. Kepler told that all the planets move around the sun in an elliptical orbit with sun at one of the foci of the ellipse. Okay, like suppose there is an ellipse, there will be two foci, and at one of the foci, sun is there, and Earth revolve around it in the elliptical orbit. So this was given by Kepler, and it was not like mathematically proved. It was observed from data. We will see it in the further slides how Kepler come to the conclusion that it is like a elliptical orbit, not a circular one. So we will go that. But and this is like you can see in the photo. This is the orbit and the point which is near the. Suppose this is the ellipse. So like it is a ellipse. So ellipse will have two foci, and at one of the foci, the sun is there. And when the planet is revolving in that orbit, when the planet is near the sun, that position is known as perihelion. And when the planet is away, that is nearby to the another foci at which sun is not present, it is known as aperihelion. Like the nearby position is called perihelion, and the faraway position is called aperihelion. So it was like that. And the Kepler gave three law. This was the first law, that the planet moves in elliptical orbit. Like this, at this moment, it seemed like quite arbitrary, but we will see in further slides why it is like uh, when we study more Newton laws, and then we will move to prove why it is elliptical. All the Kepler law, they were based on data. So they so he had some data and he made some interpretation on the base of the following data. It was not something like mathematically proved by Kepler that it was like that. All of the Kepler law will be proved mathematically by using the Newton law, which we'll be studying further in coming time. So this is the first law. So the second law was like law of area. this is quite a new thing for you guys. Like, what is radial vector? What is area vector? You don't know right now. So radius vector is nothing. Now it is just a pointing vector. Like this is we want to point something. We draw from a specific point. Like this is the origin. We want to point at a body. We just draw a vector and say this is the radius vector. Nothing else. Radius vector is just like a position vector. So the radius vector, it states that the second law of area states that the radius vector of a planet sweeps equal area in equal interval of time. Okay, so let me elaborate it. Like this is a planet. So see, this is a planet revolving in elliptical orbit. So a planet is revolving in elliptical orbit like this. Planet is revolving in elliptical orbit like this. This is here. Suppose this planet was initially here. Okay, and then it moved to there. It took around time t, which is here 1 month. So this is like suppose the origin. We draw a sorry fault. So this is like the position vector. Okay. So this is the initial position vector. This should be straight line. So and this is the final position vector after time interval t. So this area enclosed, this is A2. Okay. And this is another, like see, you can see this radius vector is small, even though this is like small, r initial dash, r final dash. So you can see like this is nearby to the planet, so the gravitational force will be more, and this will be like rotating like this. So it will sweep this much, it will go from here to here, it will go from here to here in 1 month. And in the same case, it will go from here to here in 1 month. So the time interval is same. So these areas will be equal. This is mostly based on conservation of angular momentum, as you can see in further lectures, as it is a like a central force. So the torque is zero. Hence, the angular momentum is conserved in all the central forces. Like how the force acts on planets. The force will be like in this direction. Mostly the gravitation force in that direction. So angular moment in a simple in nutshell, angular momentum will be conserved. And this is what we get after using that criteria. We get that the area will the radius vector will sweep equal area in equal interval of time. Okay. And so the third law of orbits, it stated that the square of the time period is directly proportional to the cube of the semi major axis. Let me write it. It states that t square is directly proportional to a cube. So let me show a ellipse first. Like this is the ellipse, you know. This is the longer side. This is the longer one, and this is the shorter one. This is we call as A, the semi-major axis, and this is we call B, the other length, A and B. So the time period, that is the time taken to complete one revolution, is the square of it is directly proportional to the cube of the semi-major axis. So, so as I was talking about, like these are not mathematically proven law. These were obtained from the data. So, like there were two scientists. So Tycho Brahe, he lived from like 1546 to 1601. So he observed through a naked eye. He owns an island actually. On that, I think his friend gave him an island. So on that island, he observed various planets using his naked eye only. He makes observation regarding the position of the planets, including Mars. So he, using his naked eyes, like on this date, the position of planet is this. On that date, the position of planet is this. Using his naked eye only, he made that list of observations for a longer period of time. And then after when Kepler came in, so like Kepler come in, and then he used his data, and then formulated his observations. Like for example, if you have a circular orbit, then like it will be its time period will be constant throughout the motion. Obviously, in elliptical orbit, it will be constant. But like you can see, like this is moving in a circle, in a locus of circle. But Kepler see that it is not moving in locus of circle; it is moving in ellipse. When he plotted those points in like on a plane, and he seen that this is not a circular orbit, this is a elliptical orbit. And also he had the data about the position and their distance. So he measured the distance of the major axis and minor axis of the ellipse and related it with the time period. So these observations later came to be crucial for the formation of the Newton law of gravitation, which form basis of the multiple theories and multiple innovations in coming time. So Newton law of gravitation. Like we all know, like Apple fell on Newton head and then he formulated gravitation. But it was not like that. Apple fell on Newton head and Newton told that the gravitational force is F is equal to G m1 m2 by r square. It was not like that. So he did he thought something. At that moment, a thought strike him, which later lead to the formulation of Newton law. It was not like an instantaneous formulation. First, he saw that the apple is falling. So he related it with like the similar force which is forcing the moon to rotate, the centripetal force which moon is facing, so that it rotates in a circular orbit around the earth. So he thought that the apple is also facing the same force due to which it's falling. Like the cause behind the centripetal force and the cause behind the falling of gravity, falling of the apple is the same. He came to know about it. So then he find some. So it is just a common scientific process. First, you make some assumption, make some theory, and then look for some experimental validation for those theories. Then he calculated acceleration of moon. Like we know the time period of moon. So he just like am is equal to omega square r, where omega is like time 2 pi by time period. We know it. Omega is equal to 2 pi by time period, and acceleration of moon is nothing but omega square r. Like this is earth and this is moon, and this is the centripetal force. So this was his observation. So then he calculated like AM came to be about 0.0027, and then he calculated the gravity, the acceleration by which the apple was falling, which came out to be 9.28, as we all know. So then he thought, what is the relation? So he formulated the data and see that acceleration was 1 by r. Then Newton formulated his famous inverse square law. The acceleration was proportional to 1 by r square, where r is the distance from the center of Earth. Then Newton formulated this famous law, A proportional to 1 by r square. So this was like that. So what was the Newton statement? That any particle of matter in universe, any particle, not just planet, like even two pen and my phone, these are also attracting by force of gravitation. But but the extent of the force is very less. That's why they are not getting like stick, or they are like, or gravitational force is always attractive in nature. It is not never repulsive. Like in analogous, it is there is an electrostatic force and there is gravitational force. Actually, they are just like copy. Mostly in the two chapters, gravitation and electrostatic, the fundamentals are same. Like you do the same thing. You find the fields, you find the energy, you do like dynamic systems, etc. So Newton's law of gravitation says that any particle in the universe attracts any other with a force varying directly as the product of masses and inversely to the square of the distance between them. So it was the proportionality. So he said that F proportional to m1 m2 by r square. And to remove the proportionality, there must be a constant. So we come to a new constant, which was G m1 m2 m2 by r square. Now we have, so then come a new constant, which was then came a new constant G. came to be known as universal gravitational constant. What was its value? The value was 6.67. Let me check its value. Into 10 to the power minus 11. 2.67 into 10 to the power minus 11. What about the unit? Let us check the unit. So the formula is F is the, let us take the unit. G came out to be, so Newton meter square per kg square. This is the unit of G. Newton meter square per kg square. And what about the dimensions? So let us take dimensions on both sides. Taking dimensions, we have G. So F for force is ma. So mlt minus 2 is the dimension of the gravitation, and r squared is like l square, and it is the below is like m square. So it is dimension is like m minus 1 l cube t minus 2. This is the dimension of universal constant G, and this is the unit. Let me write it. Newton meter square kg, or kg inverse meter cube second square. You can write it both ways. But Newton, mostly in Newton, we consider it to be a fundamental quantity. So this is like this. So now as we know, we have the formula F is equal to G m1 m1 m2 by r square. But we want to, like, instead of doing it single step directly force computation, we want to do it in two steps. First, we like there is a mass. First, we say there is a mass m. We define a term that there is an invisible field around it. So m1 creates an invisible field around it, having different value at different position. As force is a vector, field is also a vector. Field is like a new quantity. We define a new quantity. Like m1 generates a field around everywhere. It m1, and it expand around, like it expands from it to like infinity. There is a field, and at every point, this field has unique value. As Because it may even have the same numerical value, but the direction is different. So at every point in the space, it has a unique value. So we define force. We find force in two steps. First, we define a field which has unique value in every point in space, and then we find the force. So like this is like the field. We say like this is the field. This is the direct. This is like field vector there, there, there. Anything. Field vector is like this. We define field vector by E, and then we force. Then we say force to be m mass mass of the object. We want to find the force, like this. What is the force experienced by this mass? So this is the force, and this is the electric field at that point R, where we want to find where is the mass is situated. Like m1 is there and m2 is here. So this is field. So this is field, I think, and force, both are vectors. So now F is ME. Like now we look for the unit electric field. What is the unit of this? It is nothing. Newton kg inverse. Now we look for the dimensions. It is nothing. It is just what F by M. Electric field is nothing. It is F by M. F by M. Electric field is F by M. So suppose we want to find, we don't know the field, but we know the force. So we place our test mass there. This is the test mass, and we find the force over there, and we just divide the force by the mass. We get the field at that point. Okay, like that. So for dimensions, it is mlt minus 2. It is not. It is just the dimension of electric field is L T minus 2. So this is like that. And we have another definition of electric field which says that the force experienced by a unit by a particle of unit mass is defined to be the electric field at that point. This is just the another definition of the gravitational field. So earlier, what we used to do, like we want to find the force. We needed the both mass, but now we first find field due to the first mass, and then just multiply this field with this force to get the force. So, for example, suppose we know that this is m1. Let us give us example of 2 point mass m1 at distance r. It is m2. Suppose we need to find force as m2. We know that the force at m2 is nothing g. Now we need to find field due to the mass m1. So what it will be? Force on m2 divided by m2. So it will be like g m1 by r square. G m1 by r square. It will be the field due to a point mass m1 at a distance r from it. This is the field. So the value of the field will be same around the circle of radius r as the value of, but the direction at the every point will be different. So that's the thing. Now we have a next parameter. So let us write the vector form of the electric field, gravitational field. So as it is the vector, we need to write everything in vector form. But we like for the sake of like we are doing in 1D, so we like it like so m2 our distance, and we want to find like the electric field, the gravitational field due to the mass m1. So at distance r m2. So if we draw the position vector, this will be like this because the position vector is always pointing in this direction. So this will be the direction of the position vector and the corresponding unit vector r capital. This will be the direction of the position vector. This will be the direction of the like the unit vector. But we know that gravitational force is always attractive. Gravitational force is always attractive, unlike the electrostatic force, which if there are like charges, they will repel, and unlike charges, they will attract. But in gravitational forces, they are like always attract. Two mass, how can be there like a negative mass and positive mass? It is not possible. So they always attract. So we want to find the field in vector form. So it will be like G m1 r square minus r cap. This will be direction of field. So there will be a minus sign for the field. And if we multiply like denominator and both numerator by r, minus r into r cap will turn into minus r vector, and the denominator turns out to be G m1 r cube r vector with a minus sign. This is the electric field. So now this is the gravitation field. Uh, we were at like there when there are systems, we need to like discuss two aspects of it. First is like the force aspect. What is like the force, uh, and the second aspect is the energy. We need to like what is the energy. Suppose there is a force, and if that force did some displacement, so it will do some work. So we need to dissect the second aspect, which is the energy. So as many of you will have been familiar with the gravitation energy, which is the like mgh, as you have seen in the work power energy chapter or in like earlier classes. There is a gravitational potential energy which is equal to mgh. But this is like how it came. So we will see like why it is like mgh and other thing as well. Uh, so first we start with how we get that to the potential energy. So we know that the gravitational force is conservative force. Like so, work work done is equal to minus delta U. That is the change in potential energy. U, which is U final minus U initial, and with a minus sign, it turns out to be U initial minus U final. So it is like that. So suppose, mm, let us see, we have a simple setup. We have mass M1 here. We want to bring a mass M2. This is its final position at a distance R from mass M1, where various initially it was at very far distance. Let us say M2 was at infinity. It was its initial position. So as both mass were like far apart, so there were the initial potential energy was zero. Now we need to find the final potential energy. So how do we get to that? So it is nothing. It is just the U initial is zero. So U final is nothing minus work done. Negative of the work done in moving the charge. So the final potential energy is nothing. Just the work done in moving the charge from infinity to that point. So what is the formula of work done? As the force is variable, we need to integrate with a minus sign. The initial position was infinity. The final position was R. So, and the formula is like force is G M1 by R square. It is the field, and into M2, the mass, and it is the net force experienced, and into dr. As it is collinear, so F dot dr is just like force. Force is in the direction of displacement. So this is the direction of the force. This is the direction of the this is the direction of the force, and this is the direction of the displacement. So it will be nothing. So it will be like cos 180 degree. So which is, what is the value of cos at 180? It is minus 1. So we have like infinity, and minus minus will get plus. So we have G M1 M2 R square dr. And when we see like this is 1 by R square, so the integration will be like 1 by minus 1 by R, and 1 by infinity is 0. So the value is like M2 by R with a minus sign, because the integration will give us. So the final potential energy of the system is this. Now we will do a simple exercise. So let us do just a simple exercise. Uh, suppose this is a rectangle. This is M1, M2, M3, M4. So we need to, this is a rectangle. This length is A. This length is B. We need to find the potential energy of this system. So to find the potential energy, suppose we first bring the mass M1 from infinity. So we so it will become with like a zero potential energy. There will be no restraint. It is just like coming without any force. So it will be zero. And then the mass M2 comes. So when the mass M2 comes, there will be like it will interact with M1 which is at distance A. So it will be a minus sign, M1 M2 by A. Okay. Now in the presence of M1 and M2, we now bring M3. So first it has have interaction with M2 M3 by B. Now the interaction of M3 and M1. The distance between them is the length of the diagonal, which is under root a square plus b square. M3 will be a square plus b square. Now we add more terms. Now M4 is being brought in the presence of M1, M2, M3. So first the interaction of M1 and M4 at a distance b. Now the interaction of M2 and M4. And now we have the interaction of M2 and M4. We have the interaction of M3 and M4. I think I got all the terms. It will be A. So this will be the potential energy of this rectangular system. In the similar situation, you can be asked to find the potential of any kind of configuration. It might, we will see further application, how to calculate the field, how to calculate the potential energy of the system in the further exercises. Now, so as in this is the potential energy of the system. So we discussed like gravitation potential energy. Now we like in the similar way we defined electric field. Now we define the gravitation potential. So gravitation potential energy, like for E, E was defined as work by m. Both were vectors. In the similar manner, we defined gravitational potential V as gravitational potential energy U by mass. So it is just an analogous, and we will see the dimension. It is like joule per kg. This is energy, joule per kg in SI unit. If we want to like exaggerate more, so it will be like kg square. Kg will be gone. The unit will be like meter, meter square, second inverse square, second square. So, and when we look for the dimension, it will be like L square T minus 2, the dimension of the potential, dimension of the gravitation potential. So now V is equal to U by M is the gravitation potential. Okay. So for a point mass, the potential can be defined as V is equal to Gm by R at a distance R. It is its potential. At any distance R, it will be the potential due to this point mass. Gm by R. Now we move towards the last topic we are going to cover in this class. So this is like the relation between the electric field and the potential. So one of the major aspects of this chapter is like interconversing between things. So if you are giving a potential, you can find the field, and if you are given a field, you can find the potential. We have done like the first one. We have finded the electric potential. The potential using the given field like G M1 M2 G M by R square. Using that, we have finded the field. So now we have defined V. Let us write in like the elementary form, differential form. So dV, elemental change in the potential, is equal to elemental change in the potential energy divided by the mass. Now du is what? Du is work done. So du is nothing. We say F dot dr. What is F? We can define F as m into E. So it will come up minus. Obviously, the work done is the negative of the potential energy, so there will be a minus sign. So minus F dot dr by m. So we write F as me. Got cancelled. So we are left with like dv is equal to minus E dot dr. This is a very important relation. This is like one of the most important relation in entire class 11-12. It is also valid in electrostatic. This is dv is equal to E dot dr. very important. We can integrate both sides from point 1 to point 2 to get like V2 minus V1 is the integration from 1 to 2 minus E dot dr. If we integrate both sides, we will get this equation. V2 minus V1 is equal to minus E dot dr. So also if we like to write in 3D, which is if we like the dr vector like this, we will get dx. We write in 3D notation like dx x cap, dy y cap, dz z cap, and electric field as, and similarly we can write it. So the dv will be like summation e, it will be like minus ex dx minus ey dy minus ez dz. So this will be like this. So there can be two cases, like we can be given a potential, we can find the field using this formula, or if we are given a field, we can find the potential using this formula. So like this is it for this class. So thank you for the class. You have been a very nice listener.